Hey, okay, so for today, I decided to go ahead and write out the notes first because we do have a lot for this section, and that way you're not having to waste time watch me writing. And also, you're going to get a little bit of a bonus of how to factor ax squared plus bx plus c. But this video is actually going to focus mostly on rational functions, how to get vertical asymptote, horizontal asymptote, oblique, all the things from the equation and how to get the graph, but also we're going to work backwards, go from the graph and get the equation from it. All right, so let's dive in. The first thing you're going to want to do when given the equation is try to factor it, okay? Because we want to see if anything cancels, we'll have what's called a hole. And a hole is another word for just removable discontinuity, because what that would look like is, say we had a line here and at x equals 2, there's a hole, but the line keeps going, right? So the only time we're actually taking our pencil off the paper is for the hole, and then we just keep going. So if we say there's a removable discontinuity, that means we can put a point here. So like, let's say that's 2, 1. We can plug a point in right there, and now you have a continuous function. All right, after we do that, we're going to find the y-intercept. So how to do that is you set all the x's equal to 0 and solve for y. Pretty simple. Now the x-intercept, you're going to take your numerator, set it equal to 0, and solve for x. We also call this zeros of the numerator in shorthand. So instead of saying set numerator equal to 0, just find the zeros of the numerator. Okay, vertical asymptote, you're going to do the same thing except with the denominator, because that way you have 0 in the denominator, which means it is undefined. Okay, so that means we have a vertical asymptote wherever the denominator is undefined. So that's simply the zeros of the denominator. Now your horizontal asymptote gets a little bit more tricky. So here we're actually going to look at the power, or we also call it the degree, of the numerator versus the denominator. Okay, so if the power or the degree of the numerator is less than if the power or degree of the numerator is less than the denominator, you have one horizontal asymptote at y equals 0, which is also called the x-axis, okay? If it's equal, you have one at y equals, and then you're just going to divide the leading coefficients. So let's say we had y equals 4x squared over x squared. Okay, the powers are equal, so we have 1 at y equals 4, because it'd be 4 over 1. All right, now if the numerator is greater than the denominator, you do not have a horizontal asymptote, but you have to check for a slant oblique, but also called a slant asymptote, but it's also called an oblique asymptote, okay? And now how to find that is you're going to actually use long division to divide the denominator into the numerator, and then the result, you're going to drop the remainder, and that top result is going to be what is your oblique or your slant. Okay, the next thing they're going to look at is your domain. And this normally is going to be all real numbers except the vertical asymptote and any holes that you had left over from step 1, okay? Now there's two different ways to write your domain and range, okay? The first one is called set notation. So you use these little face brackets. So this says x is all real numbers except x cannot equal in whatever your vertical asymptotes or holes are. Now you can always have more than one vertical asymptote. So if you have more than one and you have a hole, just keep going. Okay, then there's interval notation, where we say the domain is -infinity to whatever, union whatever to positive infinity. If you've got a couple different vertical asymptotes, you could even have -infinity to the first one, union another one to another one, union another one to positive infinity, okay? And also your range, exactly the same thing as your domain, except now it's all real numbers except your horizontal asymptotes, okay? So again, set notation, y is all real numbers except y cannot equal blank. Also, one thing I forgot to cover up here in the domain, you could also have a graph that might look like here and here type thing. So your range here would actually be y is greater than 0. Okay, so it really just depends on your graph. And then interval notation, range is, and then follow the range along the domain, because this will definitely change. Okay, let's do some examples. Now, if you did not write out of all the notes that we just went over, I would highly encourage you to go back and write those out, because instead of getting you a little dizzy, seasick, moving my paper back and forth to look at the steps, you'll be able to see those steps on your own. All right, so first example, f of x equals x squared minus 2x minus 3 over 3x squared plus 7x plus 4. Sorry, I needed a little bit more room. All right, so the first thing we're gonna do, again, number 1, you have to factor. All right, so what are factors of -3 that add to -2? -2. So that's 3 and 1. So the 3 is going to be negative. So we have x minus 3, x plus 1. All right, so now we have to deal with this one. So when we have an a that does not equal 1, we have to do factors of a times c that add to b, okay? It's not as simple here where when a equals 1, it's just factors of c that add to b, okay? So the first thing we do, 4 times 3, 12. Okay, we need that to add to 7, okay? Fortunately for us, it's 4 and 3. Okay, now what we're gonna do is break up the 7 into the 4 and 3. All right, so first we start off writing 3x squared plus, and it doesn't matter which order you do these in. So 4x plus 3x, and then finish out your equation. Okay, now what you're gonna do is put imaginary parentheses around your first and second term and your third and fourth term. Now you're going to factor out what you can. So here we look at the 3 and the 4. Well, we can't factor out anything except a 1. So now we look at the variables. So we can factor out an x. So 3x squared divided by x, 3x. 4x divided by x is just 4. And again over here, well, we can't factor anything out, so we're going to factor out a 1. And then 3x plus 4. Now what we're going to do essentially is to factor out this whole parenthesis from the entire equation, okay? So that comes out 3x plus 4 and x plus 1. Now we have our factored denominator, okay? So we have 3x plus 4, x plus 1. All right, now we notice that this x plus 1 cancels, okay? So right here, we need to say we have a whole at x equals -1, okay? And we need to remember that when it comes time to do our denominator later, or our domain later. Okay, so the first thing we're gonna do is rewrite our polynomial without the factor that got canceled. So we have x minus 3 over 3x plus 4. All right, so number 1 step was factor. Number 2 is to find your y-intercept. So we're going to set x equal to 0 and solve. So y-intercept. So we have -3 over, that's 0, so -3 over 4. X-intercept. You set the numerator equal to 0 and solve for x. So equal to 0, move that 3 over, so x equals 3. Oh, that equals 1. All right, so the next thing we find is our vertical asymptote And to do that, we look for the zeros of the denominator. So set the denominator equal to 0. Move the 4 over and divide by the 3. Negative 4/3. Okay, now we look for the horizontal asymptote. All right, so that is when we look at the power of the numerator versus the power of the denominator. Okay, so here we notice they're equal because it's 1 and 1. So if they're equal, you divide the leading coefficients. So y equals 1 over 3, so 1/3. Now for your domain, I'm going to use interval notation. So it's negative infinity to, remember we have a hole at -1 here, and we're looking at the vertical asymptote. Now this is technically 1 1/3, so it's going to hit that first. So negative 4/3 union negative 4/3 to -1 union -1 to positive infinity. All right, now for our range, okay, it's usually all real numbers except for your horizontal asymptote. So negative infinity to 1/3 union 1/3 to positive infinity. Okay, now we're going to grab our calculator and double check. Okay, so now let's double check our domain and range. Now your calculator is probably newer than mine, so it's not going to show you this vertical asymptote line right here. So we can see the domain goes from negative infinity, stops at the vertical asymptote, stops at the hole. Now since we didn't plug in the original equation, our calculator is not going to calculate that hole, okay? So, and then it just keeps going to positive infinity. Good, okay, range. Yep, it still goes from negative infinity, stops at the horizontal asymptote, and does go to positive infinity. Okay, I hope you don't mind, but I erased our work from earlier because I need space on this paper. All right, so our second example is going to be f of x equals x plus 5 over x squared minus 7x plus 12. Okay, and first things first is go ahead and factor. So factors of 12, that add to -7, so it'll be -4, -3. X plus 5 over x minus 4, x minus 3. All right, so next thing we do is find our y-intercept. Okay, and to do that, set all the x's equal to 0 and solve. So let's just go back here, up here and use this. So it's going to be y equals 5, 0, 0, and 12. Okay, x-intercept. Set the numerator equal to 0 and solve. So x equals -5. Then for the vertical asymptote, zeros of the denominator, okay? So x equals 4 and 3. Horizontal asymptote, okay? And again, we're looking at powers of the numerator versus denominator. So numerator is 1, denominator is 2. So the numerator is less than the denominator. So we have 1 at y equals 0. And now let's look at domain. This time I'm going to use set notation. So we have x is all real numbers, except x cannot equal 3 or 4. Okay, now for our range, let's look and see what our graph looks like. Okay, so we see our vertical asymptotes here at 3 and 4. And if you notice, our graph does not go below the x-axis. So our range is actually going to be from 0, our horizontal asymptote, to positive infinity. So that's y is all real numbers. Y is greater than 0. Okay, next example, f of x equals x squared minus x minus 6 over 2x plus 2. Okay, again, first thing we do is factor. Okay, factors of -6, that add to -1, so it'll be -3 and 2. Okay, and then here we can factor out a 2. Okay, nothing really cancels, so we are done with that. All right, y-intercept. Okay, set x equal to 0 and solve for y. So -6 divided by 2, -3. X-intercept. Okay, that's the zeros of the numerator, so 3 and -2. Vertical asymptote. Look at the zeros of the denominator, so that'll be x equals -1. Horizontal asymptote. All right, the degree of our numerator is greater than the degree of our denominator, so we don't have a horizontal asymptote, but now we need to check for an oblique, okay? So here we're going to do 2x plus 2 x squared minus x minus 6. Okay, so how we do this, especially because now we've got a greater number out here than we have under here, okay? So the easiest thing to do is say x squared divided by 2x, okay? So that's 1/2. Now x goes into x squared once, subtract the powers, so 1/2 x. So we'll put 1/2 x here, okay? So 1/2 x times 2x gives us x squared, pull it under, change the sign. 1/2 x times 2 gives us just x, pull it under, change the sign. Okay, that cancels. -2x minus 6. Now, what do we multiply 2x by to get -2x? -1. Okay, so -1 times positive 2x gives us -2x. Pull it under, change the sign, positive 2x. -1 times 2 gives us -2. Pull it under, change the sign, positive 2. That changes. That cancels, so it leaves us with -4. Now, with the oblique, remember, we're just going to drop this remainder anyway, and this is our oblique, also called slant. Sorry, I forget. Okay? Okay, so now for domain. Okay, and I'm going to go back to using interval notation. So we have -infinity to our vertical asymptote of -1, union -1 to positive infinity. Now let's look at our graph. Okay, so here you will see the vertical asymptote and also the oblique, right? You can see that straight line here that the graph does not cross. But what we notice is when we go up the range, right, there isn't a time where, since we don't have a horizontal asymptote, we have all real numbers, right? So our range is all real numbers, or can be written as negative infinity to positive infinity, right? Okay, for this last one, you're going to be given the graph, and now you're going to have to work backwards and find the equation of this graph. So first, let's get all of the components together. All right, so we're just going to do a rough sketch over here because we know we have a numerator and a denominator. Our y-intercept is +6. Our x-intercept is -4. We have a vertical asymptote at x equals 2 and a horizontal asymptote at y equals -3. Okay, so first things first, let's deal with this x-intercept first, right? Because we know the x-intercept is the 0 of the numerator. So we're going to put x plus 4 in the numerator. Okay, so that's number 1. Number 2, we're going to look at our vertical asymptote because those are the zeros of the denominator. So we know we have x minus 2 in the denominator. Okay, the next thing we're going to look at is our horizontal asymptote. Okay, we have one at -3, which means our powers are equal, and when we divide the leading coefficients, we get -3. Okay, so we'll put -3 out in front here. Okay, so now what we do is we're going to check our y-intercept. Our y-intercept is what we use to make sure we have the correct answer. Okay, so let's multiply this out. We have -3x minus 12 over x minus 2. Set our x's equal to 0, so they go away. When we divide here, do we get +6? Yes. Okay, so now we know that our equation is accurate.